Hi guys, I hope all is well. Okay, today I'll be in STTN124. I will be explaining chapter 17, which is unit 6, contingency table, the easiest chapter, contingency table. So when we look at the outcomes, you must be able to fit a contingency table on a theoretical distribution, okay? You must interpret the basic results regarding the goodness of fit analysis or the fit test. Okay, let's check. Just do this. Just put this one here. Okay, the first one here, it's a frequency table. So, but I can't talk about the frequency table because I believe that most of you guys are aware with the frequency table on how to get the frequency table and so on. Because most of you guys, when you guys were doing last semester, you did a STTN111 and you did the frequency table. So this one, yeah. And also you can start with the introduction. Okay, so when we look at the introduction, for e.g., suppose that we have the three political parties. We have political party A, B, and C. Just do this. We have political party A, B, and C. So now here, it's a question. Are the proportions the same in 2019? So since we said we have the political party A, B, and C, the political party A, it's 60%, B 30%, and the political party C is 10%. So when you add all of them, you'll get 100%. Okay, so now here it's a question. They say in 2019, a researcher sample of 1,000 voters and ask what is their preferred party, which is A, B, or C. So if we look at the proportions here, they say that the 60% comes from the party A, which is the 600 out of that 1,000. The 60% of the 1,000 voters, the 30% and the 10%. But when we look at this, I think for some students who are saying that they were struggling with this chapter, the most important thing here is to know this whole thing. I'm going to explain everything, to know this whole thing. So this is what you do here. Let me just start from here. So because on this one, I think there will be a question similar to this one. I think I saw it somewhere. With this one, yeah. I'm going to explain this whole thing on how to get those things. So if you check, when you are dealing with the contingency table, you remember the hypothesis testing from the previous chapters. So here, step one, you formulate the null and alternative hypothesis. Okay? Step two, it's when you specify the significance level and write down the correct formula of the test statistic. Then step number three is when you calculate the test statistic. Step four, you state this in rule, you calculate the p-value. But here, you will be given a p-value. In this case, you will be given a p-value on this one. And then step number five is when you draw conclusions or you interpret or you make a decision. So let's check this one. This is an example. So now this example, because this is the contingency table, né? Remember, with the contingency table, you will be given what you call the observed frequency. This 320, 208, 240. This is a table. It's a category A, B, C. Party A, Party B, Party C. You're also given the observed frequencies. Here, 320, 280, 240. Now, let's look at step number one, where you formulate the null hypothesis and alternative hypothesis. So, always, when we are dealing with the contingency table, when we formulate the null hypothesis, we always say that the proportions are the same when we formulate the one for contingency, I mean the one for this contingency table. We always say that the proportions are the same under the null hypothesis. Then now, under the alternative hypothesis, we always say that the proportions are not the same here. HA, which stands for alternative hypothesis, the proportions are not the same. That's how you formulate the null and alternative hypothesis here. Okay, and then this an example. Let's look at the example. Example one. They say that in 2009, three political parties A, B, C, they got 60%, the other one 30%, the third one 10% votes. Okay, respectfully. In 2019, a researcher takes a sample of what? This is very important, 840. So meaning n is equal to 840, the sample size. Here, n is equal to 840. Well, just yes. N is equal to what? Is equal to 840. And ask, what is their preferred party? Now look at this now. The observed preference of 2019 is provided in the table below. Determine if the proportions in 2019 are the same. Now, the aim here is for you to at the end, is for you to interpret or to draw a conclusions whether the proportions are the same or they are not the same. Because remember, when you look at the null hypothesis, we said that the proportions are the same. The alternative, the proportions are not the same. So remember what is, you will always be given the observed frequencies, but you'll have to find what we call expected frequency. So this is what you do. You remember what I said, ne? You will be given the probability. So before I look at the steps, step 1, step 2, step 3, already I can make a conclusion by just looking at the probability and the level of significance. Without me calculating the test statistic, I can just make a conclusion. Why? Because I can use the p-value and the level of significance to make a conclusion. Remember, from the previous chapters, we said that if the p-value is less than the level of significance, what we do? We reject the null hypothesis at a certain level of significance. But if the p-value is greater than the level of significance, we failed to reject the null hypothesis at a certain level of significance. So here in this case, we have the p-value of 0,0001 and the level of significance alpha as 0,01. So we're going to compare the p-value with the alpha, the level of significance. So here in this case, what we're going to do here, we're going to say between this 0,0001 and 0,01, which one is the bigger one? Obviously, the bigger one is 0,01, the alpha. So therefore, p-value is less than alpha. What do we do? We reject the null hypothesis. Then after, we make a conclusion. Yeah, that's it. But now let's just do the steps and how to get the expected and so on. But I just gave you guys an idea that by just looking at the p-value and the level of significance, you can just make a conclusion. But okay, let's look at this one. So here, HO, remember we said that the proportions are the same. HA as the alternative, the proportions are not the same. So here we look at the scenario, be like, okay, they said that in 2009, they said in 2019, the second statement, in 2019, a researcher takes a sample of 840 people and asks, what is the preferred part? So obviously, our statement under the null hypothesis will say that the 2019 voters' preference are the same as in 2009. Or you can just that the proportions are the same. Then the alternative, it's the opposite of that one. Because since we said under the null hypothesis that the proportions or the 2019 voters' preference are the same. So when we go to the alternative, we say that they are not the same. That's how you formulate the null and alternative hypothesis. Now this is what you do. Step 1, you are done. Step 2, you specify the level of significance and you write down the correct formula of the test statistic. So here it is. How do you specify the level of significance? You'll always be given alpha. It's either they can give you alpha as 5%, 0,05, 10%, 0,1, 1%, 0,01. So here we say that if you reject the null hypothesis, it means that, but before, let's just look at this table here under the reality. We say that the reality, if the null hypothesis is true, and our decision, we say that we do not reject decision, it means that you are taking a correct decision. And now, if our decision, we say that the alternative, we say that we reject the null hypothesis, it means under the decision HA, the alternative is true. It means that we are dealing with what we call the type 1 error, because they can ask you about type 1 and type 2 error. But under the reality, if the alternative hypothesis is true and our decision, we say that we do not reject the HO. Please be careful of this. Look at this. We say that, let me start with this one here. If under the reality, we say that if HO is true, then our hypothesis is true, and the decision say that HO is true, And our decision, we say we do not reject. It means that we are making what we call a correct decision. And if our reality, we say that HO is true, but the decision, we say we reject the null hypothesis. And HO is true under the reality. So it means that the decision will be the alternative hypothesis will be true. Therefore, we're dealing with what we call the type 1 error. But under the reality, if then the alternative hypothesis is true, and our decision here, we say that we do not reject. It means we're dealing with what we call type 2 error. But okay, let's just see. Let's check. Let's check. Already we know that we'll be given this one. Okay, this is the formula that you guys are going to use to calculate the test statistic under the contingency tables. Ne? This is the formula that you guys are going to use. X squared is equal to this thing, OI, it stands for observed frequency. The EI stands for expected frequency, divided by the EI, where the EI is expected frequency. So here, you remember I said you'll always be given the observed frequency. The only thing that you need to find is expected frequency. Okay, let's check. So the formula says x squared is equal to the summation of observed frequency minus expected, closed brackets, to the power 2 divided by expected frequency. Okay, let's check. Under the step of how to calculate the test statistic. So here, we were given the observed frequency, 320, 280, 240. Now, this is what you do. Remember, you were given a hint or a scenario, maybe let me just say a statement. On the statement, they said that you have party A, B, and C. Under the party A, it's 60%. The party B is 30%. Party C, it's 10%. Now, for you to calculate the expected frequency, you only need two things. You need the value of n. And here we said that n is equal to 840. You need n, you also need those percentages. So it means that for me to calculate the expected frequency of party A, I'm going to say that 840 multiplied by 60% on a calculator. That's how you do it. You get the expected frequency of party A. For me to get the expected frequency of party B, which is 30% here, remember I need the value of n, I also need the percentage of that party B, which is 30%. So it's 840 multiplied by 30%. Here it is. Whereas 30%, you know that it's 0.3. And then you get this number. For me to get the expected frequency of party C, which now it's 10% here, I need n, I also need the percentage of party C. So n is 840 multiplied by 10%, and 10% is 0.1. So it's 840 multiplied by 0.1. You will get 84. This here are the expected frequencies. Because they can say, calculate the expected frequencies, the expected frequency of party B. You remember, you need n, you need the percentage. That's how you calculate the expected frequency. Once you get the expected frequencies, it's going to be easy for you to calculate the test statistic because now you have the expected frequency, you also have the observed. And remember what we said, that for you to calculate the test statistic, you need the observed frequency, you also need the expected frequency. Then you are done. So let's see. Here are the expected frequencies. So look at this now. This is observed. This is expected, observed, expected, observed, and then this is expected. Here, guys, there are two ways of how to calculate the test statistic when you are dealing with the contingency table. It's either you will be given a scenario where on that scenario you will be given the percentages, where on those percentages you will have to calculate what we call expected frequency. After I just showed you guys on how to do that. Once you get the expected, obviously observed here, it is 320, 280, 240. Once you get the expected, it's going to be easy for you to calculate the test statistic. Another way, you will be given a table. On that table, you will have to calculate the expected frequencies using the values that you are, the totals, what you call the row total multiplied by the column, but I'm going to show how to do that on a later stage. So now here, that's how you do it. Remember we said that x squared is equal to observed frequency minus expected. We divide everything by expected. So 320 minus 504 inside the brackets to the power 2 divided by the expected 504. This is what I did here. The second one, 280 minus 252, close the bracket to the power 2, divide by 252 here. The third one, 240 minus 84, inside the bracket to the power 2, divide by 84 here. Then just add everything. And here, I think they got maybe 360. Yeah, as the test statistic. Okay, so now you formulate the null hypothesis and alternative. You specify the level of significance. You write down the correct formula of the test statistic. And after you calculate the test statistic, this sort of calculate the test statistic, you need to check if are you given a table like where you are not given any percentages. But on that question, I think it's under 6.2 or 6.3, but I will explain it later stage. But on this one, you were given a scenario. On that scenario, you were given a table, one table of observed. So for you to calculate the expected, you will have to use those percentages and also the sample size to calculate the expected frequencies for party A, B, and C. So since now you have calculated the test statistic, to get the CN rule, we're going to use the p-value that we were given, 0.0001. Where is it? I think I talked about this one. Okay. We're given a p-value of 0, here it is. Where's that thing? Here, 0.0001 and also the alpha of 0.01. So here, this is very important. Once you master this part, you're good to go. Remember, we said that the null hypothesis, the proportions are the same. Alternative, the proportions are not the same. So, and I said, if you reject the null hypothesis, if you say the p-value is less than alpha, you reject the null hypothesis, it means that the proportions are not the same. Because why? You rejected the null hypothesis. It means you rejected that statement of the null hypothesis. I agree the statement of the null hypothesis says that the proportions are the same. It means when you rejected that statement of the one that says the proportions are the same, it means the minute you reject that one, you accept the one so the proportions are not the same, which is alternative hypothesis. Only if you reject the null hypothesis. But if you fail to reject, or if you do not reject the null hypothesis, it means that you do not reject anything. You do not reject the statement of the null hypothesis. It means that you accept that statement because the proportions are the same. So please be careful of that. Okay, let's see. Let's see. We're given the p-value 0.0001 and alpha of 0.01. Here in this case, p-value is less than alpha. What do? We reject the null hypothesis. And what did we say about the rejection? We said that if we reject the null hypothesis here, it means that the proportions are not the same. Here it is. You make a conclusion. You see, we rejected the null hypothesis. So, and after we rejected, we say now the proportions are not the same. Or you can use the statement, the voters 2019 preference are not the same. Or you can just say that the proportions are not the same. Yeah. So that's how you do it. So this is just an example. That's the other thing. There's another question here, exercise. We're given another percentages. So now you saw the only thing that you need here is the value of n. And I believe that you are given that n. Let's see. Wrote a mixture of the value of n. Get this whole thing. To get the value of n, you can also add the observed. The observed, yeah. And you just use you multiply by the first percentage to get the expected frequency. So that's how you do it. I think here you see it is, you see they got 1,000. So I think if you're not given and try to add this, or add the observed frequencies, I think they will give you 1,000, because now if now we add 320 with 280 and 240 and 160 thousand. Yeah, so if it happens that you're given a scenario and then on that scenario you're given the value of n, just add your observed frequencies, then you'll get the value of n. So this one, if it's the same thing. Yeah. So I hope now you saw how to calculate the test statistic, how to formulate the null hypothesis and make conclusions, interpret under 6.1. Then 6.2. Let's look at 6.2. This is the one that I was talking about. Then this one, so where you're given a table now. You remember I said two ways to calculate the test statistic. The other one, you'll be given the percentages. On that one, you have to find the expected frequency using those percentages and also using the value of n. This one, you're given a table. So let's look at this part on how to calculate the expected when we are given a table. Okay, let's see. Okay. You saw on that one where you were not given a table. That one you were given the percentages, and also you were given, it was a one table where you were given the observed frequency. So here in this case, you are given a table. You're not given any percentages. You are given a table. You saw that on that one, the previous one, 6.1, when we formulated the null hypothesis and alternative, we said the proportions are the same under the null hypothesis. Under the alternative, we say that the proportions are not the same. Now, you need to be careful of this. Now, the minute you move to the one where you are given only the table, the statement of the null hypothesis and alternative, they will change. Now we say that the two variables are independent of one another. Because we are dealing with the two variables. Because we're given a table. That table, it has x and y. The variables that they are talking about is x and y. So under the null hypothesis, we said that those two variables are independent of one another. But under the alternative hypothesis, we say that the two variables, they are dependent, or the two variables are dependent of one another. That's how you formulate the null and alternative hypothesis under this method when you're given a table. That's how you formulate the null hypothesis. Then from step 2, 3, 4, and so on, still the same thing. You always be given the probability, you will always be given the alpha, and so on. So let's look at the question. You see, you will be given something like this. Determine whether the variables, which is the exercise and the endurance, are independent. We're given the p-value of 0.2359. We're also given the alpha of 0.01. By just looking at the p-value and also the alpha, I can make a conclusion, okay? Since now the p-value is 0.23 and the alpha is 0.01, it means that the p-value is greater than alpha. And if the p-value is greater than alpha, what do? We fail to reject. It means we fail to reject that statement of the null hypothesis theory that two variables are independent of one another. We fail to reject that statement. It means we still accept the statement of the null hypothesis because we don't reject, we fail, or we do not reject the null hypothesis. So step one, we know how to formulate. This is how you do it because it's x and y. Those two variables, the variable exercise and the endurance, are independent of one another under the statement of the null hypothesis. But under the statement of the alternative hypothesis, the exercise, the statement, the x, which is the exercise, and the endurance, they are dependent of one another. That's how you formulate the null and alternative hypothesis. Look at this table. You see, when you compare this table and you also compare it with this one, you see on this one, you were given this. Compare these two questions, you'll see that they are different. On this one, you're given the percentages. You will have to calculate the expected frequencies using those percentages and also using the value of n. But when you look at this one under 6.2, you are only given the table only. And even when you formulate, those statements are not the same. The other one, you said that the proportions are the same. The other one, you said that the two variables are independent of one another. You see, the one where you're given only the table, like this one, it's when you are dealing with the independent dependent. So here, that's how you formulate the null hypothesis and alternative hypothesis. You specify the level of significance. Already you're given, ne? You're given the level of significance 0.01, which is 1%. You write down the formula. The formula is still the same thing. Same thing. The only thing that will change here is the expected frequency formula. On the previous one, we were using n multiplied by the percentage, ne, to get the expected frequency of each party A, party B, party C. Here in this case, we are given a table. We'll have to find what we call, for us to use the correct formula of the expected frequency. You look at this, you might think maybe this is difficult. Like, nah, which one am I going to divide this with? You see y1, y2, cat1, cat2. This is what you do. This is how you do it, ne? To calculate the expected frequencies. This is the method that I'm going to give you guys, ne? It's what you call, you're gonna say the expected frequency is equal to the row total multiplied by the column total. But some they just say the column total multiplied by the row total. That's how you do it. You divide everything by n. That's how you do it. Now, let's go back to the table so I can show you something. Look here. You are given a table. Check if your table has the totals. Here are the totals. Let me just change the color. Maybe to red. Here are the totals: 60, 40, 20, 120, 90, 30. Ne? These are the totals. Make sure that your table, if it doesn't have the totals, calculate them. You have to create your own table. Like you have to, if there are no totals, calculate them. Maybe you only given this one, this one, this one. You only given these things here. You have to calculate them yourself. But here we're given. Ne? Now let's calculate the expected frequency. You see here they were saying cat 1, cat 2. Let's calculate it. Ne? That's how you do it. Look at this. Let me just change the color. Maybe I can use this one and put this. This is how you do it. Ne? Remember I said the row total multiplied by the column total. Ne? We're going to start with this one of no. This one of no. Ne? We're going to start with the one here no. Remember the row total multiplied by the column total. Divide everything by 120. So we say now the EI here. The EI, I want to put everything here. The EI is equal to the row total multiplied by the column total divided by n, which is 120. So now we start with the one for no. What is the row total for no? It's 90. Ne? But what we can do here to make sure that students they don't get confused here, can just do it like this. We start with the column total. The column total multiplied by the row total. This is the formula that you guys can use. The expected frequency, we only use this formula when you are given only the tables. Ne? You only use this formula. But if you're given the percentages, it's easy for you to calculate the expected frequencies because you only need n, you also need the percentage for you to get the expected. And once you get the expected, you are provided with the observed. So it's easy for you to calculate the test statistic. Now here you are given a table. Number one, check if that table has the totals. Here in this case, we're given the totals. We say that the formula that we are going to use, but others maybe they might also prefer this method, the one for cat1, y1, x1. But on my side, this is the method that I normally use for my students. We say that expected frequency is equal to what is the column total multiplied by the row total divided by n. We start. Let's start with the column total. We start with the one for low. We start with the one for low. What is the column total for no? Low. It's 60. So 60 multiplied by, we go to, remember 60 multiplied by this one. We go to the row total of 90. Row total of 90. So 60 multiplied by 90 divided by n, which is 120. You get this. Now, we do the same. When we go to the moderate, we take what? The column total, which is 40. So it's going to be what? 40 multiplied by what? By the row. By the row total, which is 90. Divide everything by 120. Here it is. We do the same with high. Remember, now we're under this row total of no. So that doesn't why we do this. We take this column total, we multiply it by 90. Everything multiplied by 90. Because we are still under the row total of no. Under the high, we take the column total of 20. The column total of 20. We multiply it by what? By this here. By 90 divided by 120. Here it is. Now, this one, it was under the no. The no. We had to use the row total of the no. If we move to the yes, here, let me just change the color here so that you can all see. If we move to the one of the yes, we do the same thing. We say the column total of 60. Now, because we are done with the one for no, we move to the one of the yes. The row total of the yes is 30. So we're going to say, remember, column total multiplied by the row total. 60 as the column total multiplied by 30 of the row total. Here it is. Divide everything by 120 because the 120 is the total. We do the same thing. We are done with the low, we move to the moderate. Moderate, the column total is 40. 40 multiplied by, we're done with the no. Now we're under yes again. We use the row total of the yes, which is 30. So 40 multiplied by 30 divided by 120. 120 is the total. we get the answer. We're done with the moderate, we move to the high. 20 as the row total, multiply by 20 as the column total, multiply by the 30 as the row of the years. You divide by 120 as the total. That's how you do it. Once you get this thing, the expected frequency, it's gonna be easy for you to calculate the test statistic. Let's see. You see, here are the expected frequencies. Here. Now, what does the formula say? It says that observed frequency minus the expected frequency, closed brackets to the power 2 divided by the total. I mean, divided by the expected frequency. So here, it's going to be easy because now we say 43 minus 45. Inside the brackets to the power 2, you divide everything by 45. Ne? Plus 29 minus 30 inside the brackets to the power 2, divide by 30. You do the same thing with the 1 year 5. What are you going to say? 2. Obviously, 2 correspond with the 1 5. 2 minus 5, it close the bracket to the power 2 divided by 5. That's how you calculate the test statistic. Once you get the test statistic here, then you're done. You see? So that's how you calculate the test statistics of the contingency table. Two ways. The one you're dealing with the percentages, the other one you're dealing with only the table. So you just need to understand this here. This thing here. Here. Let's just look at the other question. Maybe there's the other questions that I can show you guys. Then after I'll talk about this one. Just need the other question. This one question. Okay, so wait, just want to show you something. Because the one with the for conclusion, that one I believe now you saw how to do it because just compare the p-value with the level of significance. You just make a conclusion. So now look at this now. This is an exercise. A university conducted a study to determine if a person's typing speed is dependent on if the person is left, right-handed. A sample of people was drawn, and each person's typing speed was classified as below average or the average or above average. Okay, the following contingency table was constructed. Remember what I said? Check if the contingency table has the totals. But when you look at this one, it doesn't have the total. So you will have to find the total here, total here, total here, total here, total here. You also have to find the last one, which is the n here. Let's check. I think they did it here. You see, it's very important. Now they will calculate the totals, you see. Because on that question, you're not given the totals. This is how you do it, ne? Once you get the total, it's gonna be easy for you to find the expected frequencies. How do you do it? Remember, column total multiplied by the row total divided by n. N here, we're going to divide our expected frequencies by 200. So we're going to say we start with this one, the one of above average, ne? Now we're going to multiply by 94. It's gonna be like column total is 43 here multiplied by 94 divided by 200. You get the answer. We're done. Now we go to which one? We go to 157 multiplied by 94. We divide by 200. You are done. Now we are done with the above average. We move to the average. We do the same thing. 43 multiplied by 84 divided by 200. You are done. 157 multiplied by 84 divided by 200. You are done. We are done with this. Below average. 43 multiplied by 22 divided by 200. It means you're gonna get the expected frequency for this one. You are done. 157 multiplied by 200 divided by 157 multiplied by 22 divided by 200. You get the expected frequency for this one. You are done. Thinking that's what they did here. You see, 43 multiplied by 94 divided by 200. Here it is. You see, 43 multiplied by 94 divided by 200. You get this one. Expected frequency for this one. The minute I say 157 multiplied by 94 divided by 200, I'm getting the expected frequency for this one. The minute now I'm done with this, I move to the average. I say 43 multiplied by 84 divided by 200, I'm getting expected frequency for this one. You are done. 157 multiplied by 84 divided by 200, it means I'm getting the expected frequency for this one. You see, just like that. And then you also get the expected frequencies. You're going to use them to calculate what? Data statistic. And then, yeah, just try this one and see if you can be able to get the test statistic value. Yeah, what's the other one? It's I think it's this one. This one that I need to explain. What you call the Yates correction. So in the case of 2 multiplied by 2 table, ne? 2x2 table with expected frequencies of less than 10. Let's see. Look at the formula. It says x squared, where it's alpha is equal to summation of observed frequency minus expected frequency, but you divide everything by expected frequency, minus 0.5 to the power 2. You ask yourself, with this one, how do you see that we're going to use the Yates correction? They will tell you. Because now look at this. Calculate the Yates correction test statistic. Remember they said 2 multiplied by 2 table, 2x2 table. So with this one, let's look at this example. Ne? You see with this one, to calculate the expected frequencies, let's try to use the method for the one that we're using there. But obviously to get the test statistic, you will have to do what? You'll have to minus by 0.5. Here it is. You say this one minus this one minus 0.5. This one minus this one minus 0.5. But to the power 2, get 0.5. But when we look at this, let's say now we're under treatment A. Remember, we want the expected frequency. So we're going to say what? Column trial multiplied by the root trial. So 105 multiplied by 257 divided by 501 to get this one. Okay, let's see. Let me just check. It's 105 multiplied by 257 and then divide by 501. So on my side, I got 53.86. Here it is. Same method to get this. Now I'm done. Now I move to the next one. 396 multiplied by 257 divided by 501. 501. Just do this. 501 to get this one. You'll get 203.14. Now I'm done with the treatment A. I go to treatment B. I'm going to use the root total. So it's going to be 105 multiplied by 244 divided by 501 to get the expected frequency for this one. Also this one. Then, but now when you calculate the test statistic, you'll have to minus by 0.5, minus 0.5, minus 0.5, and so on. That's how you do it. Then to get the test statistic. But the procedure is still the same thing. Because you'll be given the p-value, you're going to use the p-value, compare the p-value with the alpha, you make conclusion. The most important thing here is to check, are you going to use the method where you are given the percentages? Are you going to use the one where you're not given the percentage, you're only given the table, where you have to, by saying the row total multiplied by the column total divided by 2, divide by the n, or this one of the Yates. Obviously, I think this one, they will tell you that this is based on the Yates correction. How about the test statistic of the Yates, like this one here, or the 2 by 2 table, you see, 2 by 2. So yeah, and then you get the test statistic and so on. So yeah, that's how you do it. So I think part 2, I'll explain 6.3, this one, the one with one variable. Yeah, I'll explain this one. Let me just check here. Let me just check if I need to explain this one or it's still the same thing. It's yeah. This one, I think we talked about this one. This one of the 2 variables. Let me just check. The independent one. The variables are independent. They are dependent. We also talked about also this one. We also talked about this. You look at this one. Yeah, so you're given the percentages. It's going to be easy for you to calculate the test statistic because you're just going to find the expected frequency by using the percentages, and then you get the test statistic. Let's see if the same thing. Even this one, I think we talked about the Yates correction. Now we are just only given the exercises. Exercise number 3. Yeah, I think there's no need for me to explain 6.3. Look at this exercise. This one. 200. Look at this. Monday to Sunday. You're given this. Look at this. This one. So by just looking at the state and alternative hypothesis and so on. So by just looking, you see you're given this. Observed is 200. But when you look at this, you see, they say 200 multiplied by 0.143 to get the expected frequencies. I believe that you're given a statement where you have to multiply everything by 0.143. But obviously, like, I think if you check the previous question papers or maybe the exam question paper, you'll see that the question will be more specific. So yeah. The most important thing here is for you to see which, yeah, this question is based on this. It's like this one, you see, dimension independent. So you know that the method you are going to use is this one. If you see this one, you're only given the totals. You will have to find the trails by yourself. Total for this one, this one, this one, this one, and this one. And once you get the totals, now you can calculate the expected frequencies using those totals. Row total multiplied by the column, I mean the column total multiplied by the row total, like this. Yeah. So this chapter is easy. This interesting chapter. So yeah, let's to get distinction with this chapter. Yeah. So yeah, thank you guys. Don't forget to subscribe to my YouTube channel so that you can see more videos of STTN124. So yeah, part two, I think I'll do it this week. The one where I'll be explaining the maybe just 2024 exam question paper, 2023 exam question paper, just looking at chapter 17, the contingency tables. Yeah. So yeah, thank you guys.